Then. So the topic today for database and memory office hours are why column store scans are faster than row store scans. Again, we have Shasank Chavan, who's a vice president of in-memory technologies and basically one of the lead development managers for database and memory. Myself, I'm a database and memory product manager. And then we have Gregg Christman also on the line today. He's going to help moderate the questions and make sure we try to get all of the questions that we can answered. So the agenda for today is basically to go through a few slides, kind of cover why column store scans are faster than row store scans. I have a short demo for you, and then we're going to turn it loose for questions. So I apologize for the late start and the technical difficulties with Zoom here, but we will go ahead and get started. Safe harbor statement. Database and memory, just to review from our last session, in case you're not aware, database and memory provides columnar formatted data in addition to the traditional row formatted data. So that's kind of where we get into the question of why is this columnar formatted data that's in this new in-memory column store as part of database and memory, why is that so much faster than the traditional Oracle row store data that's in the buffer cache, which you might be more familiar with. And so we are going to try to cover that. The gist of the two formats is that I like to tell people that we could have called this the analytic database option, because it's really about analytics. Columnar formatted data is very, very good for fast scan analytics. We'll tell you why, versus the row store, which is very good for, hold a second, for OLTP. And so database in memory, it's a pure in-memory format. You don't have to populate the entire database in the column store. You get to pick and choose the objects you want to populate. And the data is then formatted in columnar format. We have a couple of questions that we'll get to that cover things like, what about DML? And DML is kept transactionally and simultaneously in sync with the row store. We do that similarly to the way we keep indexes up to date, but it's very, very much, much faster because we don't generate any undo or redo because it's a pure in-memory format. Oops. So let's get right down to it. So in the buffer cache for row formatted data, in order to get to, say, column 4 in our example here, we actually have to read each database block into memory and then scan across each column, or each row, I should say, to get to the column we're interested in. So we actually have to read quite a bit of data. And that's kind of the first reason that row-based data is slower than columnar formatted data. In the case of getting column 4 from the column store, we only have to access the actual column data itself. And then there's some other technical improvements or features that we've added into the column store that make this scan of that column or columns much, much faster than they would be if we hadn't done that. Again, the column store is allocated through the SGA. We talked about this in the first office hours. It's a pure in-memory format. It's a pure columnar format as well. It's not persisted on disk. The row store is still the persistence mechanism in Oracle. None of the on-disk formats have changed, and none of the transaction processing has changed. The optimizer, cost-based optimizer, chooses between a row store query and a column store query. And the fact that we don't change any on-disk formats means that not only do your applications not have to change, because the cost-based optimizer is deciding does it make sense to access the data from the row store or the column store, but in addition to that, we don't change any of our existing technology because we haven't changed anything on disk. So we talked a little bit about columnar format. You only have to access the columns you're interested in that are part of the query. This avoids having to look at a lot of data that we don't need to actually look at or access, because we can only look at the columnar data that's part of the query. It's pure in memory, so we don't have to do any I/O associated with that access. In addition to that, we compress the data. Columnar data compresses very well, and we have multiple levels of compression. we typically get anywhere from a 2x to a 20x compression level, depending on the compression you choose. You can actually choose to compress individual columns at different levels, and we have multiple levels for DML. The default mem compress for query low, also have query high, and then capacity low and capacity high. In addition to that, when we populate, we actually create in-memory storage indexes on each of the IMCUs, or in-memory compression units. Again, we talked a little bit about that in the previous office hours session, and we may dive into that in a later session as well. The gist of that is, as we populate a segment, a segment populated in the column store is made up of one or more IMCUs, rather than a large contiguous amount of memory. For each of those IMCUs, each of the column values or column CUs has an in-memory storage index associated with it. It allows us to prune out data that we don't need to look at. So in the case of looking for a store ID of 8, if we're scanning our sales table for that column value or a column of store ID, we can actually skip over multiple IMCUs, access IMCUs that have a min-max value within the range that we're looking for, and possibly peek at the data dictionary and skip data if we know, even though it passes the range scan for the data in that IMCU, but the data is not there because it's not in the dictionary, we can then short circuit our scan and avoid doing any work that we don't need to do. In addition to that, we support SIMD vector processing, or single instruction, multiple data processing. Essentially, think of it as array processing. And so what it allows us to do is access multiple values in essentially one instruction cycle. This allows us to go from scanning millions of rows per second per core in the row store to being able to scan billions of rows per second in the column store. So those are the technology features of database and memory. In addition to that, the optimizer understands database and memory as well. When you allocate the column store, you set in-memory underscore size greater than 0. The optimizer then has it at its access different access plans to run database and memory type queries. One of the first things it can do is it can push filter predicates into the scan. Also, it can push aggregations into the scan. So I like to tell people the ideal database and memory scan is one that we can do strictly by accessing the data in the column store and returning the result back to the calling query. That's not always possible, but that's kind of the goal, is to be able to do all of the work that we can in the scanning of the data in the column store. An example output of that would be doing a select count, where we're able to see, we notice that we have a table access in memory full. This is actually an execution plan from an actual SQL statement. And we see down below on the predicate information that the in-memory keyword tells us that we've pushed the filter predicate for part key into the scan of the column store. And we also see in the session level statistics that our IM scan rows projected is the same number as the, unfortunately I can't see it because I've got some windows here. Let's see if I can move it, is the same number as the rows that we returned. And so that IM scan rows projected is actually a very good statistic to determine how much work was actually done during the scan operation of the query. In addition to that, we support, hash joins. So hash joins can be actually turned into scan and filter operations with the use of Bloom filters. And so that's another significant speed up in the optimizer has to use in queries that do joins. So if it can choose a hash join, it can then turn that hash join from creating a hash table, which it would still do. In addition, if there's a filter predicate, it can create a Bloom filter. It can then use the Bloom filter as a scan of the larger table as a filter predicate, as opposed to having to probe the hash table to find matches. Instead, it can use a Bloom filter, effectively turning a hash join into a scan and filter operation. First on the smaller table in the hash join, and then scanning the larger table, in this case, the stores table, creating a Bloom filter on store ID, and then pushing that as a filter predicate into the scan of the sales table. This can provide up to a 10x performance improvement over a traditional hash join. And then we have in-memory aggregation, or something we call vector group by. This provides the ability to actually do a group by, or the aggregation from a group by, in the scan of the Columnstore. This is a little bit more complicated picture here, but essentially what we have is two-dimension tables, a products table and a stores table, and they're part of a join to the sales table. In addition to that, we're doing a group by here. And what winds up happening is we use key vectors rather than Bloom filters when we create or when we scan the products and stores table. We push those as filter predicates into the sales table. And in addition to that, we create an in-memory report outline. Think of it as a multi-dimensional spreadsheet, and we do the aggregation as we're doing the scan of the sales table. Now that was all very complicated. I just kind of glanced over that. There's actually, all of these features are documented in not only in our in-memory guide and our documentation, but also in our technical white paper. There's actually a separate technical white paper that describes in-memory aggregation in great detail. And so if you're curious about this, again, I just covered the very basics of the fact that the option exists. I'd encourage you to take a look at that white paper and look at the details of what we're doing. This shows up in an execution plan as a vector group by. So why not just cache the table in the row store? And what I've got here is an example from a demo that I do, but what I'm going to do is, instead of showing you a slide, we're actually going to flip over and go to an actual demo that I have running on my laptop in VirtualBox. So this demo picks up from where we left off in the previous office hours. We've already populated objects in the Columnstore. See if we can show you that. And we've cached those objects in a keep pool in the buffer cache. And so what I'm going to do is I'm going to show you two queries: an in-memory query, they're exactly the same query, an in-memory query, and then a buffer cache query. And you'll notice that when we do the in-memory query, all of our data is populated in the Columnstore. And then we do the buffer cache query, it will all be cached in the buffer cache, because we won't do any physical reads, it'll only be logical IOs. And this goes back to actually one of the questions we got asked ahead of the session, a pre-session question about, well, what if I just cached my entire database, or maybe my schema in the buffer, in the row store in the buffer cache? Wouldn't that be just as fast? And let's see if we can prove that it wouldn't be. So what I ran initially was just showing the segments populated in the Columnstore. We notice we have bytes not populated as 0. Then I ran the first query, select the max total order price from the line order table, came back in 0.04 of a second. We see the execution plan shows us table access in memory full. And then let's look at the statistics associated with that. Notice we have all of our IM scan statistics, whoops, stuck resizing, showing us that we access the Columnstore to run that query. Our second query is a buffer cache query. What we did is I put a no in-memory hint there. It's the same query though. And notice it's going to take a little bit longer to run. Okay. Just checking the chat to make sure everybody can see this. Notice now it took 19 seconds to run that query. So that was, well, let's see what happened. Oops. So now we did a table access full for the line order table. So we don't have the in-memory keyword there. So we've accessed that table from the row store or the buffer cache. And then notice that now we don't have our IM scan statistics. And we don't have any physical reads, just session logical reads accessing that data. All of that data was cached in the buffer cache. But notice it was significantly slower. The reason for that is the ability to do SIMD vector processing, the access of just that single column against the column store, and the ability to push that max aggregation into the scan of the line order table to get that data back much, much faster than we can get it from the row store. Obviously, this is a very simple query. It's meant just to show the initial, or answer the initial question of why database and memory is so much faster with columnar data than the traditional row store. In follow-up office hours, we'll explore a little bit more about what we can do with vector push, or with predicate pushdown, with hash joins, with vector group by, and we'll also explore some of the other features. But for now, that's kind of what I wanted to catch. We're about 20-25 after the hour, so let's kind of turn this open to questions at this point.
Can you hear me now?
I can hear you now. Just like the guy on
there's nothing,
the commercial.
Currently nothing in chat right now.
Okay. So if you guys have stuck with us for this far, if you do have any questions, please feel free to ask them in the chat. We actually had a couple of questions pre-session, which I can go over. Again, the first question was, if I use the full database cache feature and just cache all of the data in the buffer cache, would that be as fast as in-memory column store? And I think we've shown that the answer is no, it wouldn't be. And Oracle does have both the full database caching and the automatic big table caching, but those are row store features, not column store features. One of the other questions that came up, Shasank, are you on the line?
Can you hear me, Andy?
Now I can hear you. Great.
Okay.
So Shasank is one of our development managers for database and memory, and one of the questions that was asked was support for external tables. How does it work? And what if you want to change the file? I was wondering if you might want to tackle that question.
Yeah, so starting in 18.1, you can mark your external table, any table that has the organized external param there for in memory. The way it works is if there's any modification to the table, then we'll continue to support stale tolerated only. So we won't support any modifications to the external table. So you'll have to specifically specify a parameter that says stale tolerated is true, which then allows us to basically cache your table into in memory. So you pay the cost of loading it from the external data source as you normally would, but then we will go ahead and format it into the column store like we would any normal row heap. And after it's fully populated, you then issue a query on the external table and you'll be going directly through the column store. If there's any modifications, unlike with row heaps where we track invalid rows and then we will keep things transactionally consistent, that's not the case for external tables. So we'll continue to operate on the stale copy of the table in memory. You can always repopulate the table and bring a fresh copy of it into the column store, and then we'll scan against it.
So the message there is that there's no automatic repopulation, that you have to do that manually to get a fresh copy of that data. Is that correct?
Correct.
Great.
That's correct.
And then this is an 18.1 feature. Is that also correct?
That is correct.
Great. And then it requires the stale tolerated parameter as well.
That's correct.
Okay. And actually, folks, this one's a good question, or timely anyways, because we actually have another one of the developers has posted out on his SmartScan Deep Dive blog. If you can see, let's see, I got to share this. Sorry about that. We'll do this way. Out on his on the SmartScan Deep Dive blog, Roger McNichol has actually posted additional information about in-memory external tables and how they work with database and memory. So that's actually available the blogs.oracle.com Smart Scan Deep Dive, but you can actually get to that from the Database in Memory blog if you go to the menu and, whoops, that's not the Database in Memory blog. When I did the back before, it popped me right there. We'll get there and show you under the menu option, we have a DBIM resources. It used to be on the center page, but has now been put into the menu. And if you click on those resources, not only can you see all sorts of resources we have available, the different white papers, our in-memory aggregation white paper, but if you scroll down to the bottom, we have some other important related blogs to database and memory. The last one being the Smart Scan Deep Dive blog that Roger writes. And so if you want to or take a look at that for some more details, obviously you can also look at the 18.1 documentation online as well. Thanks, Shasank.
Hey, Andy, we have a question came in through the chat.
Okay.
So, are there any data type restrictions for the columns? For example, can we use CLOB, JSON, etc.?
Yeah, so there are. So IoTs and hash clusters are not populated in the Columnstore. Lobs are supported in the Columnstore, but only inline lobs. So out-of-line lobs are not populated. And JSON is supported, especially in 12.2. 12.1 supports JSON, but in 12.2, we actually added a special binary format of JSON, and that can be populated, and you can run then analytics, very good performance for analytical queries on JSON data in the Columnstore in 12.2. That's actually documented in the JSON Developers Guide if you want to get more details on that.
One thing I'd like to just
go ahead, Shasank.
I just wanted to quickly add on that. So even if you have a lob column that's not in memory, that's not inlined, you still will maintain the lob locator in the Columnstore. So you can still see very significant benefits within memory depending on the query. So if your query is touching multiple columns or scanning multiple columns, and some of them are not lobs and just simple scalars, you'll filter out those rows very quickly, and then you'll only apply the remaining predicates on those passing rows involving those lob columns. So even though you won't, you just have a lob locator in there, you can still see massive benefits within memory.
So you can reduce the row set first within memory, and then only have to access the CLOB columns separately outside the Columnstore. Is that
correct?
Great. Okay. Thanks. Yeah, that's a great tip.
Another question came in through chat. It says, I've in-memory implemented on a rack. I see some objects populated in both the instances, queried GV$IM_segments. What happens if we were to lose one of the instances?
So in rack, we do, to support scale out, we do a distribution either by row ID range or by partition or subpartition. So if you have data, let's just take the kind of the default case of row ID range distribution. So if you had, say, a 4-node rack, you might have close to 25% or a quarter of the data in each of those rack nodes. So if one of those nodes were to go down, then obviously, since it's in memory, that data would not be available to the query in memory. What that means is we'd have to go to the row store to pick up those objects. Now, if you have an engineered system, we have the ability to do duplicate. We have a duplicate option to the alter table or create table in memory command. And in that case, we can actually mirror object or IMCUs between different column stores in a rack environment. And then that would mean that if one node were to go down, that data would be mirrored on one of the other nodes, and you would still be able to access that data. And that's only on engineered systems. But if you're on commodity hardware, or if you haven't specified the duplicate feature, then that data would not be available. But of course, the query will still run. It just won't run as fast as if it had run if that node was still up. So the data that's in that node will will not be available. Now, if the node stays down for any length of time, I believe the restriction right now is, or the timeout is 3 minutes, then we'll look, and if there's room in the other column stores, we'll repopulate that data that's no longer in the node that went down to the other nodes, assuming there's enough room in the column store. Hopefully that answers that question.
Yep, thank you. Nothing else on chat currently.
Okay. I had 2 more questions that had come in pre-session. One was, we have lots of DML. Is there going to be fragmentation in the column store? And I'll let, Shasank, do you want to take that, or you want me to do it? To answer it? I'm going to put you on the spot there.
That's okay. No, you can go ahead, Andy. I was just muted for a second. Go ahead.
Okay. So if you have lots of DML, actually what happens is when data is updated, we actually mark the change in the column store in metadata, and a snapshot metadata unit. And so if you come along and query that data, and that data has been marked as being changed, we'll get that change data from the row store. But we actually do repopulation and trickle repopulation in the background, because the goal is to keep the column store, the IMC or the columnar formatted data in the column store in sync with the row store, if at all possible. And so what will happen is, in the background, based on heuristics that say if a certain number of column values have been changed, then we'll go and schedule that IMCU, not the entire object now, just the IMCU. An object's made up of 1 or more IMCUs in the column store. We'll repopulate that IMCU so that it has all fresh or data that's in sync with the row store. We also have something we call Trickle Repopulate, which says that if there are enough cycles available and we're not busy with repopulation, we'll even go change IMCUs or repopulate IMCUs that don't meet the threshold. But in the meantime, if there are, again, changes, if there are inserts, however, what will happen is we'll populate that data into new IMCUs. So I guess the answer is no, there won't be fragmentation within the column store, because we'll always repopulate the data into new IMCUs. The data is essentially read-only once it is populated. Going back to our first session, the column store is made up of 1 megabyte extents, and each IMCU is made up of multiple, 1 or more of those 1 megabyte extents. So when we repopulate, we just allocate new memory to a new IMCU and repopulate and replace that IMCU for the one that was that had the changes that we were repopulating to fix. Hopefully that makes sense. No other questions? I had one more.
Nothing currently.
Okay, I had one more. Looked like Shasank went back and answered a bunch of questions previously, which is great. So hopefully folks got those questions answered right away. What is the best way to get all of the tables repopulated after a restart? So remember, since it is a pure in-memory format, if the instance goes down, whether it's a rack instance or a single instance, if that data will then no longer be populated in the column store, because that's kind of part of the in-memory part of the feature. And so what will happen is, on restart, we'll have to repopulate that data. If there's a priority set, we will populate that data essentially automatically after restart. If there's no priority set, which is actually the default, then we won't repopulate until first access. Now in 12.2, though, we introduced a feature called Fast Start, in-memory Fast Start. What that does is allows you to create or to enable Fast Start by creating a new table space dedicated to the space for the column store, and we'll essentially, what we'll do is we'll checkpoint the column store format. So all columnar, compressed, with in-memory column stores, or in-memory segments, storage indexes on it, on the data, in the format that it's in the column store. We'll checkpoint that to disk, and then if we have to repopulate based on a restart, we can repopulate that already pre-formatted data into memory. And that's kind of about the fastest way you can get the column store data repopulated, is to literally read it off of disk in columnar format and put it right into memory. And that was introduced with 12.2, called in-memory Fast Start. Hopefully that covers that question.
Actually, I have a question now for you, Mr. Andy.
Okay.
So getting away from stepping back from the techie stuff for a little bit, I'd be really interested to know what the typical use cases you've seen with database and memory for some of our customers.
Oh, that's a good question. So since it's database and memory is focused on analytic reporting, analytic processing, naturally data warehousing is a very good use case for database and memory, because typically folks are running lots of reports against very large amounts of data in their warehouses. BI, business intelligence type applications, key performance indicators, dashboards, especially since we can populate not only tables, partitions, and subpartitions, but materialized views can be populated in the Columnstore. Now with, as we mentioned earlier, the question about external tables, that also opens up the world of big data to database and memory, because now you can actually use or populate some of your big data into the Columnstore and run analytics on not only your big data, but your Oracle data as well. It's also very useful for mixed workload environments. Not necessarily pure OLTP, because we won't speed up DML statements. We won't speed up inserts, updates, and deletes, because we're really talking about analytic queries, scanning data. But in mixed workload environments where you have reports that you're running against your OLTP data, database and memory can be significantly more efficient at doing that. We actually have a demo out on OTN that was done with the real world performance team that shows an OLTP system, or actually a mixed workload system, but the workload was broken up between OLTP and reporting, and it shows that database and memory reporting doesn't affect the OLTP workload, the performance of it at all. Doesn't affect the performance. What this means, translated, what that means is you can do real-time analytics. You can actually run analytic queries on your actual OLTP or real-time data in real time without having to wait for it to be extracted to, say, a data warehouse, or maybe a decision support system, or some kind of a data mart, or an operational data store of some kind. You can actually run those queries right on your OLTP or transactional data, and it frees you up to be able to run queries that you might not be able to run today, simply because you don't have to create a bunch of indexes. You don't have to worry about the I/O footprint of running those queries, and those queries are run much, much faster than they would without database and memory. You think, does that cover it there, Greg?
Yeah, thank you very
Sure.
much. Nothing new in chat currently.
Okay. So we can, I don't actually have, I think I covered all of the questions that I got ahead of time. So we can wait a few more minutes to see if anybody has any questions. Otherwise, looks like we might wind up wrapping up a little bit early today. I was just scanning back through some of the other questions that we had that Shasank answered to see if there's anything else we might have missed. It doesn't look like it. So with that, if there aren't any more questions, give you another minute or so if you're shy. Here we go. Here's another question. Does a higher level of compression, sorry, Greg, I'm just going to jump right in. Does a higher level of compression come with any overhead? It does, it can. So the default level of compression, memcompress for query low, and I'll let Shasank jump in if I don't get this completely technically accurate, basically uses dictionary level encoding and some run length encoding, but typically not very much. What that means, though, translated, is we get typically anywhere from about a 4x, conservatively 2 to 4x compression rate on the default compression. We actually can operate on that level of compression, the dictionary-based encoding, directly. As a matter of fact, our in-memory storage indexes actually leverage that to avoid scanning IMCUs that don't have data that we're going to meet, or that are going to meet the filter criteria. In addition to that, memcompress for query high, it was a little bit more aggressive about run length encoding. And so that can speed up compression or queries as well, because we know we can skip over a lot of large runs of data. The two higher levels of compression, though, memcompress for query high or capacity high and capacity low, those add a zip-like compression to the data. And so that does take some overhead to decompress, but it's only on the order of maybe 10 or 15% at the outside, at the very worst case. And I tend to tell people, if you're getting a 10x performance improvement on your queries, paying a 10 to 15% overhead for the decompression is in most cases is more than acceptable for the trade-off of having more space in the column store for more data. And so the answer is yes, but it's a very small amount of overhead and typically more than offset by the advantages that are offered by the columnar format of database in memory.
One thing I'll just add really quickly is that oftentimes query high, like if you're comparing query low and query high, oftentimes query high can actually get you better performance than query low. And the reason is because with query high, even though we're focused on getting more compression, the format that we use can often be more amenable to aggregation in particular than the dictionary encoded format that we use almost exclusively for query low. And so if you are you're running a workload that's aggregation heavy, and you have these measure columns that you're aggregating on with a sum or average or whatever, oftentimes those columns would benefit with query high as opposed to query low. So it can run either way.
Great. Thanks, Shasank. That's a good point. Let me flip back just back to my presentation. I did want to point out before we wrap up, if there are no more questions, that we do have.
Oh, actually, Andy, there's one more question. You might take a look at the chat, and you'll have to see it first.
Okay, let me. So what? Oh, go back. There we go. So we do have a lot of information about database and memory out on OTN and our in-memory blog. And of course, we have our new in-memory guide. So if you do think of other questions after the session ends, before the next session, there are quite a bit of resources, quite a few resources out there. Plus, I showed you in the blog, we have the resources page available through the menu for you to get to some of the same information. OTN is a great resource. Again, the blog is I kind of consider the blog to be a kind of a portal into database and memory. So I'm going to leave that up, and then let's tackle what the question is. So we have rows. It looks like we've got an example where we've got multiple rows with multiple columns. In this case, 3 rows with 3 columns each. And the question is, how do you find out row 3, column 1, given row 3, column 2 in an in-memory scenario? Are the columns stored in an orderly fashion, sorted by row ID, row number? Actually, the columnar data is stored based on the order it shows up in database blocks. And for each IMCU, we'll read a range of blocks. Typically, with the default compression, it'll be about 500,000 rows. But the order between different IMCUs is not pertinent. It doesn't. It's not deterministic. It's just only within an IMCU. So the question is, let's go back to the example in. So now we're going to get me to change screens again. So I haven't been very good at that on this session. Let's go back and look. I can get it to go backwards. Okay, I got to get so I can get to the scroll bar. Notice that we're going to do a table access in-memory full. I assume I'm sharing that screen.
Yes, you are.
Yes. And so we're going to access all of the columns, not just particular columns. So in the case of selecting against column 1 and column 2, maybe we're going to filter on column 1 as being a certain value, and so show me all of the column 2 values that meet a filter predicate on column 1. We're actually going to scan all of the columns, assuming we don't filter out for in-memory storage indexes, basically going and doing a table access in-memory full. So that's kind of the takeaway. We're not doing row ID access. The row IDs are there so we can then stitch the relationships between the columns back together as we return it from the resulting query. I don't know if that, hopefully that answers the question from Shasank. I don't know what, Shasank, you want to chime in? Were you trying to, oh, I see, you were trying to clarify the
yeah, I was just going to, but it's easier just to speak than to type.
Sure.
So I mean, I wasn't sure if this was a question related to his previous question.
Oh, he had a previous
which was in terms of how do we find, you know, how do we project back a column based on the scan of another column? Was there some cost associated with stitching? I don't know if it's related to that, but I wanted to first just to draw out a proper representation of how the data is laid out. So it's more like what I was trying to show in that example is all the column 1 values, actually for all the rows, column 1 is laid out first, then column 2 for all the rows, and then column 3 for all the rows. And so when you do your scan or you're touching column 2 and you identify that, hey, row 3 is the one that passed for column 2, then you have this mapping or a bit vector that says, you know, column 3 passed and maybe other columns like 5 and 10 passed. Now to quickly index into column 1 to fetch out the passing rows, so you want to pass back column 1 for row 3 and column 1 for row 7, whatever it is off that pass. We have a sort of an indexing structure that allows us to get to these rows very quickly. And most of the time, if they're dictionary encoded columns, then that means these column values are all fixed width values. So you can very easily randomly access into this vector of columns to get to the column values for the passing rows. I know it's kind of hard to understand, but did that make some sense?
Yeah, I almost need a whiteboard for that explanation. That's great. So you guys are getting a treat because you're hearing from an actual developer who wrote the code. So that's a pretty cool thing. We've been very fortunate to have Shasank join us today and be able to provide those kind of explanations. Looks like he's followed up with another question, or no, actually, so the question was, did I hear that on Rack, conventional, not engineered system, we have the option to populate the objects in a preferred instance and not all of them? We actually did a blog or a blog series on Rack, and then we actually did another series or a blog post that followed up on that for 12.2. I think the question, though, is it possible to populate in a subset of column stores? In other words, if you had a Rack system, maybe you had 4 nodes, 4 column stores allocated, would it be possible to populate the data, we'll make it simple, in just one column store rather than in all 4 distributed? Because I talked about the fact that we use distribution in Rack to allow us to scale out. And the answer is yes, you can do that. As a matter of fact, EBS, the e-business suite folks, have a white paper that talks about that because for EBS, they don't allow parallelization to scan across internodes, across the instances. So they restrict parallel query to just a single instance. And so if we're scaled out, that leaves us kind of out of the picture there, because then you'd have to get the other data that was in the other nodes from the row store. So it is possible to do. In 12.1, we use services to do that. It's not simple. It's not, well, it's not that hard. We do describe how to do it there and in the documentation, but it isn't something most of our customers need to do. It's a more of a specialized case. However, in 12.2, we made it much simpler because we added a for service subclause to the distribute clause. There's a lot of clauses in Oracle in the syntax. And so you can actually assign a particular object to a service, and then you just run that particular service on the instance or instances you're interested in, and then the object will populate, and then you can access that object by connecting to that particular service and get that data from the Columnstore. So it's much easier to do in 12.2 than it was in 12.1. Again, we have blog posts that go into quite a bit of detail on how to do that on the blog for both 12.1 and 12.2. You're welcome. So there's a thank you there. So
that's, I think, all we have for the chat right now.
Yeah, okay. Other than the going back to the our additional resources, Shasank, do you have anything else you'd like to toss in? You're on mute.
Yeah, no, sorry,
Okay.
I was on mute. No, nothing else to add, thanks.
That's the great thing about office hours. They're really supposed to be kind of more informal. You get to actually talk to, real developers, folks that understand the different, not just database and memory, but I know we have a couple other office hours today. If there aren't any other questions, I want to thank all of you for sticking around and suffering through my navigation, and then the phone issues we had at the beginning. But I think we had some great questions. Hopefully you got them all answered. Again, if you have further questions, we will have look for announcements on further office hours. And of course, you can go to the blog, or my email address is there. We're always trying to help you answer your database and memory questions and make use of database and memory when all possible. So with that, I don't see any other questions. We're almost at the top of the hour. I think we'll go ahead and close up. And again, thank you very much for attending.